If we focus for a minute on the method itself, for the people that don't really know isotope geochemistry, so we take a core from the lake, could be a core from I guess the marine environment. You could take speleothems probably. Um, what happens when you from from the field to the lab to the result? What happens
Yeah.
with the core?
So there's a lot there's a lot that happens. And what's interesting with this core is this was a core that was collected in, I think it was 1996.
Mm.
My collaborator collected a long time ago. And what's nice, sometimes we don't realize it with these methods, that's a resource that will last for a long time as long as it's well taken care of. So you can use new methods, new techniques to revisit a core that's been around for a long time. And in most cases, that's not a problem. But okay, so the starting point is you go out and collect a core, and you bring it back to a lab that has the right facilities. And the key things you want to do are kind of log that core. You want to look at how the bulk sediment is changing through the core and kind of develop, a first picture of the stratigraphy and get a sense of, was it a pretty constant environment, or were there a lot of changes into what was coming into the lake? That's really important. People nowadays, we have all these nice techniques for what we call non-destructive core logging. So you may be familiar with X-ray fluorescence.
Yeah.
That's really common, and you can just do that with the core without doing any kind of sampling. It's just you scan it with an X-ray. People also do visual scanning. They do CT scanning like you do in a hospital, and that gives you a very interesting kind of 3D picture. So there's lots of different things you can do. But the most important thing to do with a core in most cases is to develop a chronology, because without knowing how old the sediments are, there's really not that much you can do with it. And on the timescales that we're interested in, the number one tool for this is radiocarbon. With radiocarbon, it's a great chronological tool, but there's also some complications with it, especially in lakes in this part of the world, because there's a lot of carbonate rock. And so organic matter that's forming in the lake could have a lot of what we call old carbon coming from kind of dissolved limestone. So you have to be careful about that. And your best tool then is to look for materials that came directly from land plants, because they will be taking carbon directly from the atmosphere. So they'll have this kind of the right radiocarbon signature for their age, effectively. So we look for things like charcoal. We look for things like seeds or little twigs. We're lucky in this lake that there's a lot of this material washing in from the catchment. So you can find lots of twigs, lots of leaves, lots of different things. So we have the ability to generate lots of radiocarbon dates. That way we know the age of the sediment. It's not perfect. Usually it can be plus or minus, if you're lucky, plus or minus 20 years, sometimes as much as plus or minus 100 years or more. So that's all good. And then you have to kind of see what's present. So if you have things like carbonates, you can do a lot of work on isotopes with carbonates. This lake, there's some, but they're not consistently found throughout the lake. And so that's where things like what we're working with, organic molecules, can be really useful, because in most lakes, there's a lot of organic matter. Organic matter is usually pretty well preserved. And then we can look at a whole range of different molecules that are produced by different organisms and that can be used as proxies for different things. And so what we do is we take our mud samples, we basically mix them with organic solvents that are very good at removing lipids. So we're primarily looking at lipid molecules, removing lipids from these sediments. So we kind of shake them up under high temperature, let them mix, and then the lipids dissolve in that solvent. We then remove that. And then we do a series of steps where we basically separate that into different fractions based on the chemistry of the different lipids. So fatty acids are different from hydrocarbons, are different from alcohols. All of these things we can separate based on their chemistry. And depending on how specific we want to be, we can do a wide range of different chemical steps to separate these different molecules from each other. So what Ben was focusing on primarily were the alcohols, because that contains the stanols. And then once he had that fraction, we just were able to inject this into a gas chromatograph mass spectrometer. And that is an instrument that separates molecules based on their different chemical properties, mostly their boiling point and also their chemical polarity. And then they basically go through a long glass tube at different speeds because of their different chemistry, and they come out the other end, and we can quantify them and identify them based on their the way their ions interact with a sorry, I'm just trying to think about the best way to describe this. Basically, just we ionize them, and then we see how long it takes them to pass through a tube, basically, and then you can figure out what their mass structure is. So this tells you what the molecule is.
Right. The best image I heard about that is like if you got three soccer balls, one that's heavier than the other, you throw them on a curve. The one that's heavier is going to go more on the outside, and then at the end you separate the three balls like this. So it's kind of that, but with smaller molecules.
Yeah, that's a great analogy. Good one. Yeah. So yeah, exactly. And so then we're able to detect these molecules. So in some cases we're doing isotope mass spectrometry. So that's very similar to what you described. In this case, it was just kind of more conventional mass spectrometry where we could detect the structure of different molecules. So we could look at this copper stannol molecule and how much of it was present in different sediment samples. And that gives us our record of, how many people were living in the environment.
Well, so then you get the proxy, and from that result, which we call proxy, we infer a population change or an environmental change or something in the past.
Exactly. And then the nice thing that you can do is you can take lots of different proxies. So we can look at that measurement. We could look at these plant wax measurements that we've done before and their isotopes and look at changes in rainfall or possibly changes in the vegetation that was living there. In a later study, Ben looked at what are called polycyclic aromatic hydrocarbons. And these are molecules that are used as a proxy for fire because they're produced when you burn wood. And so and then over time, we can kind of build up a really rich data set comparing all these things together and see how they changed relative to one another.